So, I think we learned a lot on how to deal with problems of single particles excuse me, under the Born approximation. And again, we saw how the Born approximation, the weakly scattering approximation, allows us to get very nice analytic solutions to the scattering problem. Not only that, the relationship between the scattered field and the scattering potential is a Fourier transform, therefore it goes both ways, which makes it very easy to solve inverse problems when we're trying to extract the 3D structure of the object from the measured scatter field. So this is the beauty of the Born approximation. And we looked at spherical particles, we looked at pretty much any, like cylindrical particles, cubical, any shape. Essentially, as long as you know how to write the Fourier transform along each direction, you're pretty much all set. Okay? The only difficulty is that at the end, you plug in that Q, right? So keep in mind the Fourier relationship is between the spatial coordinate R and Q, which is the momentum transfer. And that Q has theta in it and has lambda in it, right? So the only difficulty is to write that Q at the end when you plug actual numbers in terms of scattering angle, for example. Okay? It's pretty much like in diffraction. So take a Fourier transform and then to actually write the field distribution far away from the object, for example, in a diffraction problem, you have to plug in that K spatial frequency in terms of this angle. Same thing here. Do you have any questions about this? So I want you to remember what the approximations involved. So we made the Born approximation and also the far field approximation. And that ended up in a beautiful Fourier relationship. So everything is clear on that. Okay. There will be a homework 4 posted today. Okay? Sometime by the end of the day. Okay, so next we're wondering, what happens now if I have a bunch of individual particles? So we're now masters of solving scattering problems from single particles. What if I put another one? Right? And another one. And another one. Gets complicated. But if we use again what we learned in the beginning of the course about the shift theorem, it turns out that is actually very doable. So we're going to consider individual particles characterized by this scattering potential, F naught. Okay? And now, these particles are actually placed at different positions in the three-dimensional space. Okay? And how do I write the entire scattering potential? Well, like this. I take the individual particle potential and I convolve it, this is our convolution, with a delta function. Summation of delta functions. So the delta functions are these infinitely small dots, right, that give me the position. And if I take a particle and I convolve it, or the scattering potential of a particle, I convolve it with this delta function, due to the properties of the delta function, it's going to take it and put it at the position of the delta function, right? That's what the delta functions do. Yeah? Nod your head if that's okay. If not, keep staring and I'll repeat. Okay. So now, since we have more than one position, I'm summing over all these individual positions in 3D. That's it. That was the difficulty, to figure this one out. Because now, notice, if I want to compute the scattering field out of this total scattering potential, I'm going to have a Fourier transform of this thing. This is a convolution, so we know it's going to look nice, right? So let's see what comes out. Well, Fourier transform of this is going to be the scattering amplitude. Okay, so this is the scattered, complex scattered field. This is the Fourier transform, right? And it's going to be the Fourier transform of the scattering potential F naught. Yeah? So what's the meaning of this little f naught of q? Physically, what does that mean? Yes, and what does that mean?
The scattering amplitude of one particle.
Is the scattering from one single particle. So, it is that scattering from one particle multiplied with this whole thing, a summation of these phase terms. So scattering from an ensemble of identical particles looks like the scattering from one particle multiplied with a bunch of these complex exponentials, which basically what these complex exponentials take into account is that if I have these particles distributed like this, and I'm measuring scattering at this position somewhere, point P here, these little things are telling me, keeping track of these phase delays, let's say with respect to this particular coordinate system, right? This particle is going to have one phase delay, QRJ. This other particle is going to have another phase delay. This another phase delay. This another phase delay. It is an interference between all these plane waves that add up, or I should say spherical waves, okay? But in far field they become kind of plane waves. They add up coherently, they interfere at this particular point P. But they all have something in common. Why? Because they're identical. So they're all kind of scattered the same, except for these delays. You see? That's what this thing means. This particular term, notice, is actually more interesting than this one, in a way. It is called the structure function. For clear reasons. It tells you the structure of this object. The internal structure, meaning where these things are, right? Where these particles are. That's why we call it structure function. Very important property. So, this is exactly the problem in crystallography using X-rays. When you have a lattice, and now these dots are distributed with certain symmetries along the 3 dimensions. You look at the diffraction coming of this. If you don't know any of these Fourier transforms, Born approximations, whatever we've done so far, it looks like a very difficult problem. But then once you realize, hey, it's just identical particles distributed at the positions of these delta functions, the scattering field comes out to be this. You can think of this as an envelope. This is the scattering amplitude of one particle. And then it's structured by the superposition of all these waves coming from each particle. So essentially, the lattice information, if you like, in crystallography is in this structure function. Not so much in here. Yeah?
And it doesn't matter when you pick the zero.
It doesn't. Right? Why would it matter? If I shift it by all of them by a constant, I'm going to have a constant phase in front. Phase term in front. Nobody cares. Right? It will be like plus R naught here. Doesn't matter. Yeah.
Is there a difference between scattering and diffraction at this point?
Well, you'll be surprised there is no clear cut if you look at all the books. Here's my take on it. Scattering is actually a 3D version of diffraction. Okay, so when we say diffraction, we imagine how light behaves at 2D apertures, right? Even 2D objects, transparencies, whatever, right? But the physics is the same. It's actually interaction of light with the change in refractive index. Whether it's an edge, an aperture with an edge, it's the exact same physics. See, I have air in the middle and I have something at the edge. It's the exact same problem. Okay, there is momentum that changes. Okay, so scattering usually refers to a three-dimensional problem where your object is extended in 3D diffraction. You smack that down to a sheet. Okay, but keep in mind the physics is the same. Yeah, but what we always measure is actually the result of scattering or diffraction, and then superposition, which is interference. Okay? So light interaction with an object, boom, scattering. When you detect, you take all this scattering somehow, right? It overlaps at a certain point. You measure the result of that interference. If you remember the quote from Abe from 1873, he describes the imaging as a diffraction effect of an
Interference phenomenon.
interference phenomenon. Thank you. Yeah, a weird way of saying it. Diffraction effect of an interference phenomenon. Or the other way around. Interference effect of a diffraction phenomenon? No. Diffraction effect of an interference phenomenon. So imaging, this is scattering. Imaging is what? Having a certain black box here that takes all this light. Okay? If I want to do imaging, I'm going to put an imaging system here. And somehow, all that system is doing is taking all the diffracted light or the scattered light and is putting it back together. So all this light that originated from each particle is going to come back together. Okay? Scattered from there is going to come back together. And so on. If you don't have that imaging system to undo, it's like time reversing this, see? Right? Scattering, imaging. If you play it back, scattering, imaging. If you don't have that, it's a scattering measurement. You put this in, a microscope, a telescope, you time reverse that. You see? Of course, this is not a perfect black box because of that frequency coverage that we discussed, right? In the 3D case, in the scattering case, because of the Ewald sphere, that Q is actually limited, means that this is not going to look exactly like the object we started with. It's going to be a distorted version of that. Okay? But in principle, this is the difference between imaging and scattering measurements. It's kind of interesting to me that actually there are two different communities, the imaging people and the scattering people. They hardly talk to one another. I'm serious. So scattering people tend to be physicists, also another interesting thing. Imaging people tend to be engineers. And I think scattering people don't have a lot of respect for the imaging people also. I'm not sure. That I could be biased. But what's the reason we can put them all together in the same room? What's the reason from an image I cannot compute the scattered field or the other way around? Why isn't it entirely equivalent? So we established physics is the same. It's looking at this interaction between light and inhomogeneous object, right? One is measuring the scattered light directly. The imaging is adding something in between that actually reverses the effect of this diffraction. So so one is measuring in the frequency domain, in the Q domain. Imaging is measuring in the spatial domain. Why are they not entirely the same thing? Why do we have two kinds of people?
I mean, because of the physics of it, right? They're using X-rays.
No, forget X-rays. I'm talking about light scattering. Even light scattering people don't talk to light optical imaging people. Or at least not that much. So all these physicists that look at colloids, right, scattering from colloids, glass transitions, interesting things like that, rarely do they cross paths with OCT people from looking at the fiber optic imaging, I don't know, some kind of disease. They don't. They never go to the same conferences. Why is it? The very close. I mean, you see the measurements are very close.
Whereas with imaging, you're dealing with a 3D system, and depending on what your system is, it might be blocking some information. Like scattering,
Oh.
you know where atoms basically are, and you're working with 2D systems, so you can see everything.
So who's working with 2D systems? The imaging?
Scattering?
Scattering?
Yeah.
Why do you say that? My object is the same. It's the same 3D object.
But with scattering, you usually want it to be a single scattering, so it's basically like a 2D system instead of a 3D system.
No, why do you say 2D? So look at this. The structure function, let me delete the, yeah. This is the structure function. Actually, R is in 3D. So it makes a difference, going back to crystallography X-rays, because that's more clear-cut. The crystal that comes out of the measurement is always 3D. Okay, so scattering does capture 3D information of the object. There's no question about that. Notice the difference. The difference is actually not in the information. The information is the same. It's still this scattering field. The difference is I measure it here versus adding another thing that reverses it, and I measure here. But let's say if the frequency coverage is the same, if this is my angular coverage for the scatter system and this is my aperture for the microscope, the information is exactly the same. You're not missing anything. Yet, there is one difference. What happens when you detect the light right here? What are you measuring?
It has K domain,
Yes?
and then imaging people want a special domain.
Good. Okay, so we established that. So here I measure the complex field as a function of actually not K but Q. Keep in mind, very important distinction. This is Ks minus Ki, momentum transfer. While here I measure U of R. The big question is, do I really measure U, which is a complex quantity? No. What do I actually measure? I measure magnitude of U of Q squared, and here I measure magnitude of U of R squared. And that is the problem. If I only measure this, I won't be able to go back to an image plane. Okay? So if I put a detector here, my camera, and I get an intensity as a function of Q, I will not be able to generate an image out of it. Why? Because the fields are just Fourier transforms of each other, right? But the intensities are not. You see? So once I took the magnitude square of this, it means the phase is gone. E to the I whatever, phi of Q. You're right? When I do the magnitude square of this, my phase is gone. This is the big difference. So if we know how to measure the phase, either here or here, then essentially what we're doing, we're able to now merge the two fields together. Okay? So we showed in the microscopy case, for example, in our lab, that with the quantitative phase imaging that we studied a couple lectures ago, is that we can measure now not only amplitude of the field of an image, but actually the phase. Once you have that, so I have, let's say, amplitude of R, e to the I, phase of R, then I can go back with the simple Fourier transform, and I'm getting actually amplitude of K, of Q, e to the I, phase of Q. And in fact, there are some advantages when you want, there are cases when it's better to measure the scattered field directly here, and there are other cases when it's better to measure actually at the image plane and then numerically Fourier transform it. As a fun fact, last week I visited the University of Southern California, and there was this young assistant professor there, and he was He's a computer scientist specializing in problems. These problems that lack phases or lack some kind of information, and you use computers to try to. It becomes a nonlinear problem. It's an interesting problem for computer scientists. But he had one slide that was really funny. So he had Trump picture here and Hillary Clinton here. Then he took the Fourier transform of each picture. Maybe I can find it somewhere. My office is screwed up on this computer, but I'll show it to you next time. Okay, so now you take the Fourier transform of this, and you get, depending on your edges or Trump's hair or whatever, you get some Fourier transform that looks like this. But notice, this is the amplitude of K square. So this should be the intensity. And then you get Hillary's, I don't know, same thing. I mean, not same thing, very different. But both of them are magnitude square. No phase information, right? And now you swap the phase. You take the phase of Trump and you put it on Hillary, and you take the phase of Hillary, put it on Trump's amplitude. You see? And what do you think you get out? The Hillary looks more like Trump, and the other way around. Meaning that actually the spectral phase is a lot more important than the amplitude. I'm going to show you the slide next time. It makes it more clear. So I thought that was a beautiful illustration of how important the phase is. So notice, this is a numerical exercise, but physically what it means is that if I lack that phase information in the scattering plane right here, it's not optional. It's really a lot of information that disappears. You lost it. It's very hard to make an image after that. Okay? All right. Okay, any questions about this before we move forward? Hey, look at this.
The way to avoid that is to use logography.
Yes. And that's why we discussed that previously. So you have to do some kind of interferometric measurement to get the phase, and then essentially combine the two fields together. Build a bridge. Any other question? So it's pretty clear, right? Okay. So in general, I think you're learning so many different things from so many courses and people. It's very easy to get sidetracked into this fragmentation. At least in our field, there's a lot of fragmentation, like your hard disk. Because each individual area wants to be special and it looks like they specialize in something. We kind of face this danger of having fields that otherwise the physics are, the principles are essentially common. They look like they're compartments of different things, but in fact they're actually very clear. So imaging and scattering is one good example. Okay, so keep in mind, we call this the structure function, and it's actually for good reasons, because this is the term that gives you the internal structure of the object. Okay? So at the end of the day, this is what I want you to remember, that the scattering from an ensemble of identical particles distributed in a certain way is the scattering from one particle, F naught, multiplied with the structure function, with this summation of all those terms, okay? So do you remember when we did this diffraction problem, Young's interferometer? So if I have a opening like this, I think you know that we get some field that looks like that, the amplitude, right? And we did this problem. Now, how about if I had two apertures, right? Remember the result? You get the exact same thing, but on top you get this modulation. Okay, well, I have to do this. Okay? You get the cosine on top of that thing. And the cosine is due to these two plane waves interfering. You remember that? This is the Young interferometer. We don't need to write it down, right? You remember? So this gives you, this is a shift theorem. This gives you a shift that gives you a minus shift. Fourier transfer gives you e to the I k. The other one gives you e to the minus I k. Put them together, get 2 cosine, blah, blah, blah. This is the generalized version of that. So this will be the scattering from one particle, and then this is a multiplication of summation of all those particles. Now you can have an arbitrary number of different particles. And why do I call this envelope? Why do I know that this is actually broader? Why am I sure that the way, if I plot the amplitude of this, or the intensity, let's say, magnitude square of this versus Q, I can guarantee that's going to look something like this. So this will be how each particle scatters. And on top I'm going to get some kind of a mess, I don't know. Oops. It doesn't have to be a perfect cosine, but it's... So let's say I'm along direction QX. Okay? So I'm plotting K scattered along X minus K incident along X, whatever that might be. That's QX. Why am I sure that this is the internal, the carrier, if you like? How am I sure that this is actually S of QX? And this is F naught of Q. Why is it not the other way around? Why is this the final structure of the two? You know what I'm asking? Why do I call F naught an envelope? Why do I know that a priori? Why do I know F naught is smoother or broader than the other one? Huh?
It's a single particle, and so
And?
small in the spatial domain, because broad in the frequency.
Exactly. And then how do I know that this is finer than that?
Because it's a more macroscopic thing.
Okay, so I think you're right, but here's how I would say, is that S of Q is due to these interparticle distances. And these distances, let's say di, is always bigger than the radius of each particle. Yeah? That's it. This is called hard sphere models, meaning these things cannot overlap. If there are bubbles or squishy particles, actually, that gets more interesting. But so we look at particles that are relatively sparse. The distance between them, on average, I mean, always is larger than the diameter of the particle. So that means that the Fourier transform of the individual scattering potential is always fatter than the Fourier transform of all this distribution, okay? So it's really, single particle is the envelope of the signal, and the structure function is the carrier inside. Okay? Yeah? Okay. Oh, so here's my Young interferometer, but now with two particles. So these are two particles shifted up, shifted down. Fourier transform is going to be the envelope times, this is the form function, by the way, for form factor. So form and structure. This is called form, this is called structure. Function. This is the simplest structure function, cosine, right? So we know how this one scatters light, so it's this function that we discussed last time. So basically, all you do is to get the structure along whatever dimension you're looking at. For some reason, I picked this axis to be z pointing up, which is unusual, but okay. So it always looks like this, no matter how. So this assumes my K incident is like this. But how would you solve this problem if my K incident was this way? Or my particles were at this strange angle, like that? It's no problem, you just represent the coordinates, right? You rotate the coordinates, rotate the Ki. No problem, everything is the same. As long as you keep in mind Q is a vector difference minus Ki. Yeah? So if Ki rotated, no problem. I just write what it is. Yeah? If my particles rotated, no problem. I just write whatever the coordinate is. Okay? So in this case, it will be along Z, so it will be 0, 0, B over 2 for one particle, 0, 0, minus B over 2, right? That's the coordinate of the two particles. Yeah? So really with this, at this point, you should be able to solve any crystallography problem. Pretty much anything. I mean, it's all, the physics is now very easy. I'm just writing the particles with the delta function, and I put them, depending on the crystal symmetry, you can find them various combinations. But really, to solve it is now easy. You just do the convolution with the delta functions along x, y, z. It comes down to a Fourier transform. The only nuisance is to really put the coordinates of the particle properly with all the cosines and sines, and with the three angles. But it's all computation. Conceptually, to solve it is very easy. Yeah?
Can you go back to
Yeah.
from the, well, why in 6.43 there's no x and y? It's only y?
We're in the Q domain.
Okay.
Okay? So Q is angle, right?
Oh,
So this tells you how stuff scatters along this dimension far away, which is basically something to do with this angle, right?
oh, it's QC.
It's Q.
Okay.
So that's why if you know your Ki is perpendicular to Z and the particles are along Z, you will be able to write that magnitude of Q is automatically 2 pi over lambda with a 2 in front, and then it's going to be sine of theta over 2, where theta is going to be this angle. Okay? But the moment the incident field is at a weird angle, then you will have probably 2 angles, and then 3 angles. So that's why in the crystal symmetry books, you'll find actually all 3 angles, alpha, beta, gamma, right? So you can have the particles with 3 different lattices, different periods along the 3 dimensions. But the procedure is exactly the same. It just gets a little bit more involved computationally, but it's all kind of high school math. Okay? All right. Okay. Okay, 2 words about me scattering. When I was defending my PhD, my PhD was on scattering. So I had, at some point I was talking about me theory. I think some of you know the story. So I was saying, so this was developed by me, blah, 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 blah. And at that year, my friend was like, dude, that was kind of like, you're kind of a little bit praising yourself too much. But this me was 1905, so a little bit older. So he was the one to put forward the first solution for spherical particles of arbitrary size. So really, if you have a spherical particle and you know it's spherical and it could have absorption, so the refractive index could be imaginary. Doesn't matter. Me gives you the full solution for that problem. Okay, so this is the situation when we're outside the Rayleigh-Ganz regime. Okay, so our little approximation doesn't really work. Basically, so you can find, actually, if you Google, you find a MATLAB file that calculates this, actually. And there are websites at Oregon, I think, is one that has this ready to go. And I have to say that because it's so easily available, we tend to overuse it. So you'll see papers where actually biological tissues is modeled by a bunch of spherical particles, and that The only explanation for that is because we know how to do misscattering. It is not so much rooted in the reality of the tissue structure. Okay, but scattering from tissue is actually a complicated problem, so that's another reason. So, but physically, so there isn't much to say about this, but I want to say one thing, and that is if you have a particle that is big, essentially with the Born approximation, what you say is that you exclude, so I have a plane wave in, you exclude, in the Born approximation you only have this kind of contribution, so let's say scattering here, and then this overlaps with the plane wave. So you always have the light that goes through, that is the strongest component, and then you have a little bit of scattering from various portions of the sphere, something like that. Now, so this will be the Born, single scattering. In me, you allow, meaning when the particle is big and the particle can have high refractive index, there is a lot of scattering at these edges. So in that case, you are allowed to have this kind of situations. And many others, like. Okay? So multiple bounces inside the sphere. Essentially, you can decompose this into modes that look pretty much like the de Broglie atom. So you can fit a lot more, in a way, sinusoids around this, the surface of the sphere. Okay? So essentially the computation, so you can have the very high frequency one, and then the really broad one. And the Born approximation is the kind of the no, just one, okay, it's kind of the zero order version. So this summation is essentially over all these modes. So you add up all these multiple bounces inside the sphere. The bigger the particle, the more modes you're going to have fitting into your sphere. Which means the slower this series is going to converge. You're adding more and more terms. So back when I was doing my thesis, this was an issue because you had to wait long on a computer. Now there is no issue. I mean, you can make your particle as big as you want. You'll get the answer pretty much instantaneously. Okay? But I want you to give you a feeling for what this means. So it's adding all these bounces around the sphere. And clearly, the bigger the sphere, the more of those you have. So maybe some of you might have heard of whispering gallery modes. How many of you have heard of that? Yeah? Okay. What are they? Are exactly these modes that I was telling you. Well, but the story where they come from is interesting. Do you know that story? Why do they call them gallery modes?
Because there is a gallery in a church, so when in any point near the gallery it will speak. So anyone at another point near the gallery here.
That's right, because so back in the church, the way I imagine it is like these old ladies gossiping in a corner here, and everybody else would hear it all over that they didn't know any physics. That's how I imagine it. I don't know how it was, but clearly back in the old buildings that were actually, I think, built on purpose for good acoustics, you have all these modes that are actually propagating, so they are resonant to that room. Okay, so they propagate without much loss around the room. So if you put a point source here, the two ladies talking, actually they could be heard all the way over here with very little loss. So I imagine that generated some trouble. Okay, but that's what we mean by whispering gallery mode. So it comes from sound. Okay? So use me is readily available, but use it with caution, I would say. Especially in biology. Okay, let's move on and look at more kind of stronger scattering. So I mentioned in the beginning that we're pretty good at solving problems at the two extremes. It's kind of always like that. So very weakly scattering, the first order Born approximation, we just finished that, so I think we're pretty good at studying that. The results are very nice. You get analytic solutions. We're pretty good, and we're going to talk about that, at the other extreme. When the light is so scrambled, the scattering is so strong, it's like sending a laser pointer to your tissue. You'll see it kind of glows. Phase information kind of loses its meaning altogether. So we're pretty good at solving that problem. Everything in between is a mess. It's a hard problem. So somewhere between 2 scattering on average and very many scattering events, that becomes a issue. So we're looking at the other extreme now. So how do you define multiple scattering, first of all? So if I have a piece of, let's say, tissue, and I send light in, when do I decide that this is a multiple scattering medium versus a single scattering medium? If I'm an experimentalist, how do I approach that problem? So I need scales, right? What's the thickness for which this becomes a multiple scattering medium? Well, there's a scale associated with scattering, which is the scattering mean free path. So this tells you, should be defined somewhere here, but that's the average distance between 2 scattering events. Okay? So you can think of this as light scattering here, and then scattering again, and then scattering again, and scattering again, and scattering again. Something like that. Okay? So the individual steps are not the same. This is a random process. Okay? But the average L, the average distance between scattering events, is well defined, and we call that the scattering mean free path. So if the thickness of the tissue now, so I'm looking at the light coming out of this slice of tissue, if the thickness is much smaller than LS, what does that mean? So my thickness is smaller than the average distance between 2 scattering events. What does that mean? Yeah? Less scattering. So this is my weak scattering approximation. This is the Born approximation. Okay? But now when L is much bigger than LS, this is the strong scattering approximation. On average, the light scatters many times before it gets out. Okay? So that's how I want you to think of multiple scattering versus weak scattering. Yeah? Meaning that if you have a very strongly scattering medium, but you slice it thin enough, you make it single scattering. Obviously, right? All right. So there's going to be a bunch of definitions here, and I'll let you look at these by yourselves. But I want to give you the principles, first of all. Basically, because in such a strong scattering medium, you have k vectors at very different directions, over a broad distribution of directions. The phase information is actually very difficult to track. So at the end of the day, the way we discuss very strongly scattering medium is through tracking the power or the energy propagation in the medium, not so much the phase. So we forget about the phase altogether. Okay? So in order to do that, we take a elementary volume, and we really keep track of the energy coming in and the energy coming out. Okay? And that is called the transport theory, energy transport. This theory was developed in great detail in the context of nuclear physics. Are you from nuclear engineering? There we go, so you know all about that. So it's really keeping track, for example, of the density of neutrons, scattering and get attenuated and so on inside a nuclear reactor. It's the exact same physics. If you like, if it helps you, you can think of the light as a bunch of photons, as discrete particles, but you don't have to. You can just think of the energy density. It doesn't have to be particle density, okay? I personally don't use photons all that much on a daily basis, but you can. Okay, so the theory comes from nuclear physics. A lot of it was developed in the nuclear physics for obvious reasons back in the 40s. Okay, so we have a lot of definitions. So first of all, this will be the photon density. If I multiply this by h bar omega, that will become energy density. Look at this, v times mu s. So this is the velocity or speed divided by the mean scattering length. That gives you a frequency of interaction. So that's meters per second divided by meters. That's 1/2. That's the frequency, how many scattering events you get per second, which is kind of an interesting thing. An attenuation coefficient that actually includes absorption and scattering is this thing, mu. So coefficients are the opposite of length. So scattering coefficient is 1 over the scattering length. Absorption coefficient is 1 over the absorption length. Okay? So, oops, yeah, right there. So that should be meter minus 1. I should make something very clear here, that while the transport theory works for absorption as well, so meaning if you send light to your tissue, you have a lot of scattering, but let's say you have absorption, for example, due to hemoglobin or water, depending on what wavelength you use. So both of them contribute to attenuating your light. But what do you think happens when my absorption is really, really strong? In the nuclear reactor, that happens sometimes during crisis. I don't know, do you guys study this in the departments? Probably know a lot more than me on that. When something goes out of whack with your nuclear reactor, and it turns to build more energy that it can actually control, there are some crisis kind of emergency tools that you have. Among them, there are very highly absorbing materials that you drop inside the nuclear reactor. Actually, you don't drop it, actually you will lower them, right? There are these, what's the material? Cadmium is one of them? Cadmium bars? Okay. So basically you absorb a lot of that energy. So essentially you're commuting a lot of the energy from scattering into the absorption in those bars, and you kind of lower the pressure in your cooker a little bit. But my question is slightly different. What happens if my absorption now is very, very high? So I have a, let's say, a photon that goes like this, but now this will be in a low absorption. In a high absorption medium, what do I have? Very little scattering. So this thing now disappears, got absorbed. Okay? And maybe this one here disappears before it gets to scatter. So if this happens, our theory actually kind of falls apart. So multiple scattering, strong multiple scattering cannot have a lot of absorption, because as you can see, strong absorption decreases the probability of scattering. Right? If I were to draw a graph, let's say probability versus number of scattering, right? So it will be maybe For a weakly scattering medium, it will be like this, right? So 0 is the highest. For a strong scattering, it could be like that. If I have an absorption, strong absorption, the probability probably will start to look like this. It will push my scattering towards the single scattering approximation. But I cannot use the Born approximation because that approximation where I said the incident field equals, inside the object the incident field equals, inside the object the total field equals the incident field, that's no longer holding because I have a lot of absorption. Okay? So, strong multiple scattering, I don't want to confuse you. Strong multiple scattering holds really for many different scattering events. If your absorption is too strong, that situation doesn't hold, and this theory doesn't apply. Okay? So always absorption has to be below, in terms of attenuation, has to be below the scattering coefficient. All right. This definition of a photon flux. Density of photons propagating along a certain direction. Okay, there is a lot of all these coefficients. You're not going to memorize them now, but let me tell you what the equations is about. So I take that elementary volume in my scattering medium, and I keep track of how the energy density changes. That's all I'm doing, okay? So first of all, this is the change in density with time. I potentially can have a source in there. So in biomedical imaging, what could that be? What is that due to? Huh? Contrast agents. Normally fluorescence. So I inject fluorescence in a little mouse, and I'll light the mouse up. And then instead of seeing beautiful details like we see under a microscope, because the mouse is so thick, you are going to see essentially kind of blurred clouds. Okay? Okay, so those blurred, or I should say smooth distribution of intensities are governed by this equation. So that could be fluorescence. Okay? So, I can have simply photons or light coming out of that element simply due to the changing gradient. So I have more density in my elementary volume with respect to the outside. That the energy is going to migrate to kind of equilibrate that gradient. I can have photons disappear due to the absorption or attenuation, or both. Okay? So these are photons that are propagating along certain direction. Okay? So they could disappear due to the total attenuation, amplitude and scattering. And I can have a source, notice the sign change. So meaning the photon here, the photon can disappear through absorption, or it can scatter off that direction from omega to omega prime, right? Which tends to bring the concentration down. Yeah, so if this scattered at an angle is no longer in this group. But I can have the reverse. I can have light that was at omega prime and got scattered into my direction of interest. And that acts as a source. Yeah? So what do you notice? There is no phase information anywhere. This is about density, this is about energy flowing in and out, and directions are actually important. So keeping track of all these ends up in a transport equation. This is a transport equation, which is still ugly to solve, actually. So that was the integral form. This is a differential form. It's not very easy to resolve the way it is. And the most practical way to do it is to actually do one extra approximation. And that is the diffusion approximation. So we're going to assume that the angular distribution of light inside the medium is actually very smooth. Okay? So a diffuser like this, I think I mentioned to you from the beginning, this is a good diffuser, that's why we use it for the projection, is because if I look around it at different angles, I see the same thing. Right? As opposed to looking at the Born approximation scattering that we were doing earlier, if you look around the particle, you may get dark over here, right? Very bright and then dark and bright and dark. Huge differences in contrast. So the diffusion approximation is based on the fact that actually my angular distribution is smooth. It's like this. In fact, the perfect diffuser says that the angular distribution is flat. It's a Lambertian distribution. No matter how I look at it, this looks equally bright. Okay, so with that approximation, basically, it says that I have, so this is an angular flux. Okay, so how much, the number of photons coming along a certain direction per unit area per unit time is actually a constant. So it's as if I take all that energy phi and I spread it on a sphere. Okay, so it's a constant thing. That would be a perfect isotropic distribution. And then a first order perturbation. This is kind of similar to the Born. It's like the first order perturbation, but clearly in a totally different context. And this is a cosine term. So this is the current dot product onto the direction omega. So it's a cosine on top of a uniform thing. So it's a very smooth function. Okay? This is the approximation we're making. If you do this, essentially what we managed to do is to connect the current to the flux, basically. So if you plug that back into the transport equation at the end of the day, you get this, which has a name. It's called Fick's law. Okay, so it connects J with the divergence of the density. So I'm sure you've seen this many, many times before. And the proportionality constant is actually what is called the diffusion coefficient. Okay, so J divergence of phi and the proportionality constant is this thing, which is nothing more but the definition of the diffusion coefficient. Okay, so I'll let you look in more details for the derivation, but the assumption going from the transport equation, which cannot be solved analytically, it's always, you can do numerics on it and it's an iterative type of solution. If we make the approximation, then the angular distribution of the fluxes is smooth. Okay, so it's isotropic except for a small kind of cosine term. Then you're able to connect the density to the currents, and basically this is known as the Fick's law. And once you do this, you can decouple these two unknowns, J and phi, and solve for both of them. And basically you end up with this. So there is no more J separately, you see. This is a diffusion equation. So let's see what it means. d phi at dt equals, look at this. This is this divergence of phi. D is inside, D could depend on R, right? And you take the gradient of that. So this tells you the spatial change of the density, okay, so how it varies in space. You have an attenuation due to absorption, and then you have a source. And let's suppose that my d is constant. And let's write this down. So what do you have? 1 over v, this is velocity, d phi at dt, this is r and t, right? Minus, so if d is constant, I can pull it outside, d, this becomes a Laplacian of phi. Let's say no absorption. How about that? Equals the source. Or I can write it like this. Laplacian of phi of r and t minus constant d phi at dt equals the source. What is this called? I mean, we know what it's called. It's called the diffusion equation. Well, what is it reminding you of? Huh? Sure, I mean, everything should satisfy the energy conservation, no question about that. Wave equation. How is this different from a wave equation? Only first order derivative as opposed to second. Right? So if this was a field minus constant, this will be d2u at dt squared equals a source. Huge difference. Huge difference. The main difference is this: the wave equation is actually reversible in time. The diffusion equation is not. So you can think of a beam, you can focus it with a lens and then collimate it again, something like that. But once you drop ink in water, it's basically impossible to put the droplet of ink back together. Once you send a pulse of light in this tissue, and you let it propagate, it will be impossible to make your incident point source back. That's the difference between these two. One of them. This is irreversible, this is reversible. This deals with random processes, this deals with deterministic propagation. Okay? So, how do you solve this? So I'm sending a pulse of light to my tissue. Oh, by the way, the diffusion coefficient is related to here. D equals 1 over 3 mu A plus mu S. Yeah? So it relates to the scattering mean free path, the absorption, length. So let's say I know this for the tissue somehow. So I know D, and now my source is a laser pulse sent to my tissue. How would you solve that problem? Of course, you take a Fourier transform. It will be the exact same approach that we used many times to do to solve the wave equation, right? So any source, any distribution in space and time, if you do a Fourier transform of that, you will end up with, for example here, minus k squared minus whatever this constant is, c. What's the Fourier transform of d phi at dt? Plus I omega. Boom. This is phi equals s of k and omega. So phi equals s of k and omega divided by I omega c minus k squared. And you can solve it in 3D, in 2D, and so on. You can follow the Fourier transform properties that we used before. Okay? Very easy. The fact that you have this I here, it means that you don't have a resonant frequency. In other words, you don't have a signal that propagates forever. You will have an attenuation. That's what it means. Meaning, if I put a droplet of ink here, boop, that there's not going to be an oscillation that goes forever, like e to the I omega t, like in the with a point source, right? There will be a decay. Okay, it's not a periodic signal anymore. It's an overdamped system, if you like. It's like an RLC circuit that has a lot of R. Okay? One last thing I wanted to say. You're not going to need it unless you are doing, you start working on this or you do it for your research. But I think it's important to at least think about it for a second. If I have scattering with a certain particle, let's say radius r, plane wave, I measure the scatter field. So I'm trying to model my tissue as made of particles, let's say. Okay, I have a distribution of these particles. So each particle scatters in a certain way. If my particle is very small, it will scatter isotropically, like we've seen, right? These are kind of Rayleigh particles. Yeah? But as the particle gets bigger and bigger, what's going to happen? The particles start to scatter mostly forward. If you look at the particle like this, illuminated from the side, in polar coordinates, it's going to have a sharp peak forward, some structure, who knows. There's a little peak backwards, and who knows on the sides what happens. It depends on the size and wavelength and so on. But the bigger the particle, the sharper the peak forward, to scatter mostly forward. It's another result of the Fourier transform, right? That the bigger in one domain, it's narrower in the other domain. So it's narrower in the angle domain. Well, this has an implication that if I have my particles that scatter as I drew earlier, randomly like this, and we define a certain LS as the average of the distance between two scattering events. If my scattering is mostly forward, even though I have a large number of scattering events, the direction is not randomized. So LS tells me the number of scattering events, or the average distance between two scattering events. But I need to introduce another length scale that will tell me what's the distance after which the direction is randomized. Because if my particles scatter only forward, no matter how many scattering events, it will not randomize my direction. So it turns out that the new quantity that we need to introduce is called transport mean free path, which is nothing more but the old scattering mean free path. But now it's divided by the average cosine of these scattering angles. Okay? So this will be theta I. I'm sorry, 1 minus this, G. 1 minus G. So G is called an anisotropy factor. Is the average cosine of the scattering angle for that particular particle. Yeah? So, when the particle is very small, that implies isotropic scattering. And then the average cosine of that is 0. And that G is 0. That means the transform mean free path is exactly equal to the scattering mean free path. It means that after only one scattering event, the directionality of my light is lost, because each particle scatters isotropically. Yeah? So remember, this is all a statistical quantity. It means you average over the ensemble of many, many particles, right? If you average all those directions, you will get an isotropic distribution. G equals 0. But when when particles are big, then G can approach 0.99. For tissue, it's between 0.99 and 0.90, let's say. Could be 85 maybe. But for most tissues, it's between 0.9 and 0.99. Which means that transform mean free path is of the order of 10 to 100 LS's. Which means, for example, in tissue, you may have LS, the average distance between two scattering events, to be 100 microns. But the thickness for which the direction is randomized could be 10 times that, meaning a millimeter. So why is this important? Well, if your direction is not randomized, you still maintain some of that memory of the incident direction, you can actually do coherent imaging in the way we studied before with the microscope, where the phases are still important. So meaning a big G allows us to go deeper into the tissue, right? Big G means most of the light is scattered forward. So meaning in the cells, nuclei, these big particles, they mostly scatter forward. So that's good for imaging. It allows me to image deeper. But there's a hard limit at LT at which there's nothing I can do. And we're going to study actually when we get to optical coherence tomography, for example. LT is the ultimate limit. Cannot go beyond that. Okay? Okay, so what did we do today? I feel like we covered a good chunk. So first, we went back to the Born approximation, but now we looked at an ensemble of particles. And it turns out that it's very easy to solve if we use our trick with the delta functions to position the particles. And in fact, the solution of the scatter field breaks into two. It's a product of two factors. The form factor, which is the scattering as if the particle is by itself, multiplied with a factor that only takes into account all these phase terms from all the particles, all the delays. So essentially it's an interference. And those phase terms tell you what's the phase for each wave in the interference summation. So basically that allows us to solve pretty much any problem, any distribution of particles in 3D. So we're going to have fun with that for homework. Then we talked a little bit about mean theory. So this is the full solution for spherical particles, no matter how big, no matter the refractive index. Okay. And we talked about the whispering gallery modes. And then we talked about the other extreme of very strong scattering. Okay, so we went very quickly over these definitions, but basically, you forget about the phase, you keep track of the energy only, and you take an infinitesimal volume and you look at the energy coming in and the energy coming out. Okay? So you can have light that scatters off that direction, omega, that we keep track of. Okay, so that's a loss. You can have scattering from the outside into that direction, that's a plus, right? You can have light that disappears, it's absorbed, so that's a loss. And you can have a source term that pumps light into that infinitesimal volume. So this is actually still hard to solve. But if you make another approximation that says that the distribution, angular distribution of the flowing energy is fairly isotropic. So it's isotropic plus some small perturbation. This is the first term in a series. Actually, it's the first term in the Legendre polynomials, I think. So you can check them out. So I think some people call this the P1 approximation from the polynomials, first term in the polynomial series. So it's really kind of like the Born approximation. Like we always do first order perturbation theory, right, in pretty much everything we do. So this is very mildly anisotropic, okay? If you do that, essentially you connect J and phi. So you connect energy and currents, and this is nothing more but Fick's law. Right? If you have the high gradient in density, it will give you high currents. I mean, this is what we know, right? So if you have a very high gradient in one domain, it's going to give you strong flow out or in. So this is Fick's law, okay? Current versus density. And if you plug it into the transport equation, you can actually uncouple the two, and you end up with an equation just in phi. That looks like this. So the difference with the wave equation, this is only first order in time, and that makes actually all the difference. When you look at the poles or at the frequencies, before we had omega squared here, that will give me a plus omega and minus omega, so those e to the I plus omega t, e to the minus I omega t, that will be oscillating and going forever. Because we don't have that anymore, essentially you have an attenuating wave. Or I shouldn't call it wave, but you have an attenuating function. You have a decay. Okay? Very different. One is reversible, one is not. And yeah, solving for the diffusion equation can give you the probability density for path lengths in the tissue. That's a very kind of thorough function that describes the interaction with your tissue. So if you plot the distribution of path lengths, what's the probability to have this path length, that path length, and so on, longer and longer. There are interesting phenomena that happen. For example, since we have 2 minutes left, there's an interesting coherent effect that happens even if you have very strongly scattering media. So imagine I have a semi-infinite medium here, mu s, no attenuation. And I have a plane wave incident, and I have the light coming out, let's say this way, okay, scattered I. It turns out that there is a finite probability to have light scatter exactly the same way, but in reverse order. You see what I'm trying to say? So this light coming in here and coming out this way can be paired with another wave that goes in the exact opposite direction. They are perfectly matched in phase. They are in phase. Same for this one. I don't know. Okay? I can have the exact same path in the opposite direction. And notice, they are looking at the same angle. So if I make the following experiment, plane wave incident, scattering medium, so light in, light out, beam splitter here, and I collect all this light at my detector. If I plot the distribution of angles, I'm going to get a coherent peak, intensity versus theta, gives me a coherent peak that looks like that. Very, very narrow. These are milliradians. This is a coherent effect in a completely scrambled medium. It's called enhanced backscattering or coherent backscattering. Some people, some lucky people have observed this on an airplane. So if your sun is exactly behind you and you're looking at a very strong cloud, very heavy cloud, and if you're lucky enough, you're going to see a bright spot coming out of the cloud. Some people think that the reason all the saints have all this halo around their heads is because there are stories, I didn't make it up, there's reports that said that some people were able to observe that halo by reflecting in some muddy water or something like that. And it appeared as a halo that impressed everybody, and therefore they were deemed to be special people. I don't know if that's true, but I like the story. But think about this. You get the coherent, so phase, so light that is in phase coming out of a completely messed up medium. And the only reason is because you have this probability for paths going exactly in the opposite direction, being in the same in amplitude and phase. And the trick is, it only happens for very, very small angles. So if you look, this is an exaggeration. If you look at these angles, you get nothing. You get the regular incoherent part. So most of the time when you do your experiment, you miss it. You don't even look at it. You will get a Lambertian distribution like this. So this will be the coherent. So clearly, that's not 0. This sits actually on a 1, and this will be 2 for a perfect experiment, relative wise. Okay? So something to think about. Coherent effects in